Okay, welcome back. I think we should start at this point. So the second topic we would like to mention in the context of the phenomenology of catastrophic forgetting is task recurrence, and I'll show you what I mean. Hopefully, yeah. So people notice that naturally task, concept, classes recur when in long task sequences. So for instance, this is from Google Trends, an actual plot of the searches for a Christmas present. So we see that every year, starting I think October, a peak starts, and it peaks really at December, and then in January people kind of forget about it until next year. But if you look at it as a long task sequence, it recurs. Also, another example, search queries for James Bond. Usually people are not very interested in it, but some constantly. But then when whenever a new movie comes out, there's a peak of interest. And the question I think it's, which may sound trivial, but I believe it's not, is whether this can, so if we learn it in a continual learning way, whether we can compete with offline batch learning. And I'll show you an example which I think illustrates why it's not a trivial question. So let's consider task one, classification task. We have only two samples. And then we learn the max margin classifier. And then we see the second task. We learn it. Maybe, with randomly said, maybe we can convert to the second task, max margin classifier. So what happens if we see these tasks over and over again, but never together, just separately? And what we might expect to happen is that eventually, if we, at least in batch learning, if we see it enough, then we converge to a global solution. But in batch learning, it's kind of important that we never really minimize the current batch until we are pleased with the loss of the current batch. We just do one grad instead. So in continual learning, we might, I think we should, in continual learning, we might ask ourselves, if we see it over and over again, whether we can get stuck in this kind of a loop. Yeah. Okay. And I hope you are at least convinced that it's not exactly the same setting as batch learning. So even if we see tasks over and over again, like at this point in the presentation, we are not sure what will happen, whether we converge or not. And empirically, people have found recently in several papers by Stoyanov, Kosu, and Leso that recurrence do mitigate forgetting, and the models do accumulate knowledge. And so if you look at the plot, this is a plot from Leso, from less CoLLAs. What they did is that each task has a subset of the classes in several data sets, a subset of the classes, a small one. You never see all the classes together. You just see them for some fixed point of time. For one data set, you minimize it, you move to the next one. And then what they noticed is even if you use just plain SGD, no fancy method to mitigate forgetting, eventually you are going to accumulate knowledge and forgetting will diminish, which I think is very interesting finding, and also kind of answers my previous question. And it looks like you do converge to some global minimum. And analytically, it can quite nicely be explained from a projection perspective. This is a plot from our ICML 23 paper. My collaborator, Gon Buzaglo, is also sitting here. We have two classification tasks. Each task has its feasible set, the set of solutions that solve it. And then we start from some initialization, W0, and we project onto the first task solution space, and then to the second one, the third one, so on and so forth. And by doing this back and forth learning, eventually we are going to converge to the intersection of this set, and we are going to globally solve both of these steps. And this by using the projection perspective, we found out some interesting links to the projection onto convex set framework that is widely studied in optimization literature, and to the alternating projections field that has been studied for a few decades now in the functional analysis literature. And it actually allowed us to take some of the results to the world of continual learning. And what's maybe interesting is that we noticed in our papers, and also they noticed it in their areas, is that 3 tasks are already much harder to analyze than 2 tasks. So projection perspective is quite useful, but there's still this analytic difficulty that we need to deal with. And what we showed in our papers and in other papers, not from our lab, is that under random or cyclic ordering, so if we see the task either cyclically or randomly, then for continual linear regression and classification, forgetting diminishes. And we actually were able to show some rates for this. So we get some analytic guarantees by looking at it from a projection perspective. Another interesting thing that we saw is that the effect of task similarity changes with recurrence. So if you remember this plot from previously we just, Jean showed you this plot, this curve that shows the effect of each principal angle, or just let's call it an angle between tasks. And we saw that intermediate angle caused the most forgetting. But now what we saw from, in the same paper from the analysis is that if you see tasks in cycle, so you repeat the task like first, second, you see these 2 tasks over and over again, what's going to happen is that the angles that become most forgetful are the smaller ones. So initially, the most forgetful angles are the intermediate ones, but eventually the smaller ones are going to be the most problematic. Yeah. And this kind of shows that, again, task similarity has its effect on forgetting, but other factors like recurrence can have a joint effect with the task similarity. And some future direction. So one thing that I think should be dealt with first is to extend the projection perspective to nonlinear models. And we tried doing it for some time. We didn't have any luck. Maybe you'll have more luck than us. We are still thinking about it, but of course there's place for everyone. I mean, there are many ways to do it. And if we are able to extend the projection perspective to nonlinear models, what's going to happen is that a lot of convergence results will immediately follow. So we have convergence results from the POX framework or from alternating projection. And if we are able to show that nonlinear models perform projections, then immediately we get convergence results, which I think is kind of a very desired property for analysis. Another way to go is extensions to multi-class setting. So I think in theory, often when you analyze binary classification, you almost immediately get a multi-class classification result. But in continual learning, I think it might be very different. At least empirically, we know that it can get very different. You can get different behaviors from multi-class training in comparison to binary training. And finally, I think there are still interesting gaps between lower and upper bound even in linear regression. And it's interesting not only in the context of continual learning, but also in optimization context, like last iterate SGD analysis and the Kaczmar's method, if you're familiar with it, which I think is very, again, can be quite rewarding. So if you solve it for continual learning, you might make significant contributions in the optimization literature. The last question is, how do early stopping affect this finding? Someone mentioned it before, and I think we're going to, I don't think, I'm sure we're going to get back to this later. Another thing that can affect catastrophic forgetting is overparameterization. Let's start with a simple question. So before we move to the algorithmic approaches, let's just think of the models themselves. So with the plain model, we can do architectural choices, have effect on the continual dynamics and catastrophic forgetting, and the short answer is yes, maybe not surprising. For example, in an ICLR paper by Pham et al., they showed that batch norm in continual learning kind of helps forward transfer by smoothing the gradients in the current batch. And if you use replay in continual learning, you'll have in the same batch samples from previous tests and samples from the current test. And this will kind of help to smoothen the loss landscape and when you compute the running moment, but then it can cause problems when you at inference time. So at inference time, the global moments are very biased towards the last task that you saw, and then it can harm the performance in test time. And indeed, they showed that other choices of normalizing layers often improve the continual learning performance. So this is one example where architectural choices make a difference in continual learning. What we are now going to focus on is a specific architectural choice, which is the overparameterization level of the model. And we are going to ask, how do overparameterization affect forgetting? Okay, so we know generally that large neural networks often generalize better, but again, it's important to remember that it's not immediate that they are going to be better for continual learning. We know that from, let's say, the adversarial literature, that robustness and generalization often they are on the same trade. They have a trade-off between them. So the question is, what happens in continual learning? And I think in a very important paper of Mirzadeh et al. In ICML22, they show that wide neural networks forget less catastrophically when trained from scratch. So let's see some of their plots. What they did is, you can see it on the bottom. The data set in these plots is CIFAR 100, 5 classes per task. The network that we present here is wide ResNet 10, which becomes multiplicatively wider and wider. So this means wide ResNet 10, and then this means that you make it wider by a factor of 2, of 3, and so on. Sorry, 2, 4, and 8. And what they showed is that if you measure the forgetting decreases with the width of these networks, which is a very important empirical observation. Also, if you look at the average validation accuracy, so it's not that you stop forgetting because your accuracy is very low to begin with, but instead, if you look at the average validation accuracy, you can see that if you start from the narrowest model to the widest model, you do get a validation accuracy increase. So you do accumulate knowledge, you learn better, you forget less. And the next thing that they showed is that this doesn't reproduce if you just make the network deeper. So width has an important role, but depth doesn't have the same role. They also proposed some explanation for this phenomenon. They showed, for instance, that the gradients of different tasks become more orthogonal when you make the network wider. You can see it here. So if you compare the gradient between tasks, the narrowest network has, I don't think you can see the y-axis, but small angles. This means 70, and this means 90, and they become more and more orthogonal. And if gradients are orthogonal, at least in linear models, you are not going to have any forgetting, because you can think about it as the learning kind of happens in different directions or in different coordinates if you are aligned to the standard basis. And another explanation is that they show that smaller changes are needed in the overparameterized model. So when the models become wider, the model moves less in the parameter space during training. And if you remember the NTK part that I mentioned at the beginning, it means that the linearization stays more faithful to the actual model. And this means that kind of the linear analysis applies here. So it's nice to see that the overparameterized models forget less, but it seems like an effect of width rather than depth. But then in an ICLR 22 paper, Ramasesh et al. Showed that depth can also improve the continual performance, but in pre-trained models, not when trained from scratch. So what they did is they pre-trained on ImageNet, the large ImageNet, which is a huge data set. So it's a very strong initialization point. And then for continual learning, they fine-tuned it on CIFAR 10, split CIFAR 10, which is much easier, of course, than ImageNet. And what they saw is that as the models become deeper, then you get better accuracy for the first task and also for the second task. So, and it looks like at this point you have very good accuracy for the second task that you just learned, but also for the first task that you saw one task away. So you kind of stop forgetting if the model becomes deeper and you are pre-trained. what they showed next is that it doesn't happen if you train from scratch. So these two results don't contradict each other. So let's understand this graph. The gray ones mean that you train from scratch, and we see that if we move from ResNet 26 to ResNet 101, we don't get almost any change in the behavior of the continual behavior. The behavior stays almost the same for the accuracy of the first task after learning the second one, and for the accuracy of the second task. But then for pre-trained model, you could actually see the improvement. So in the shallower model, we have quite a lot of forgetting after learning the second task. In the wider model, in the deeper model, we have better performance for both tasks. So, and importantly, we kind of forget less the first data set. So overparameterization can help, but it has different effects. The depth and the width affect differently in a pre-trained model or models that are trained from scratch. And I think, as the general deep learning community moves to these directions of pre-trained models on very large data sets and very strong pre-trained models. Okay, what about theory? Yeah, sorry. Two tasks. Yeah. So I'll repeat the question. Okay, it sounds like an important question. I cannot recall exactly all their experiments right now. No, but it is a very important question. When we just consider two tasks, it almost takes us to the transfer learning regime instead of continual learning. If you consider a long task sequence, then yeah, maybe it changes. I need to reread their paper. I'm not sure. But if they didn't do it, I think it's important to do. Yeah, okay. I need to reread the paper probably. Thank you. No, but that's a good question. Okay, what about theory of overparameterization? So here, linear models are very problematic for the very simple reason that the input space is the same. So the feature space is the same as the parameter space. So you cannot just take any input and make the model overparameterized regardless. And so what people do is usually what theoreticians do. They kind of assume stronger assumptions on the model. For instance, that the data on the data model, that the data came from some latent low dimensionality subspace. So one such a paper was from Goldfarb and Hand at ASTAT 23. They showed the linear setting where overparameterization mitigates forgetting. How they did it? Uh, like I'm not very, but a little simplifying it. But roughly what they did is that the first task is xy, some metric, some label vector, and x is p-dimensional. P can be very high, but it has a latent dimension which is much lower, let's say d. And approximately it holds that for some unknown model, linear model, xw equals y. Okay. And the second task has the same label vector, but the features are rotated with a random orthogonal by a random orthogonal metric or operator. So if we try to take it to a more practical setting, then you can consider taking an image data set like MNIST and just applying some random permutation on on the entire task. Okay. And this kind of closely matches the permutation data set. And what they saw is that forgetting diminishes like square root of d over p. So if the latent space is d-dimensional and the general dimension is p, then it decreases, let's say quite, I would call it quickly, but there's a square root, so maybe not too quickly, but at least we can analytically show that it decreases. And it's very important. To me, it was a very important result. And then we kind of joined them, and in an ICLR paper, we showed that we used a more revealing data model. So instead of applying this orthogonal random orthogonal operator to the entire space, we just applied it to a small space. So in image dataset, it can be thought of as just instead of doing a random permutation, you could restrict the permutation to just a subset of the pixels. But the model, the analytic model that we use is slightly more general than this, more complicated also. And this allowed us to control the task similarity while making the model over-parameterized. And then what we found out is that over-parameterization and task similarity has a joint effect. Okay, that's the difference between a 10-minute talk and a 2 hours talk. What we found is that the over-parameterization and task similarity has a joint effect on forgetting. And when models are highly over-parameterized, we kind of get this U-shaped curve that we know from previously. But now, near the interpolation threshold, when we are just slightly over-parameterized, we saw this monotonic behavior. So it really qualitatively changes the effect of task similarity. So again, we see another case where task similarity affect forgetting depending on other factors as well. In a very new paper that I saw just last week at ICML 24, they proposed a specific feed-forward model, which is already, very promising. It's not a linear model anymore. And they showed that wider networks stay close to the initialization, like in the NTK regime. So it's an interesting property at least. And they look at it as regularizing functional changes between tasks. And they have this formula. Let's understand it. It's a very easy formula, actually. So if you get any input and you give it to the network after learning the first task, and then you give it to the network after learning the second task, then the functional change, so the change in the output that you're going to get is, and I really simplified this expression, but essentially it decays exponentially with the width being the base of the exponent. And so if you think about it, it kind of behaves like this. So it plateaus very quickly, but it doesn't necessarily, so the time that it takes to go to zero can be actually quite long. And this is just for one hidden layer neural network with value activation and SGD. They saw on multiple datasets that initially you get a very sharp decrease in forgetting, but it kind of plateaus and it takes a long time until you get zero. So this is an interesting case where over-parameterization do help you, but perhaps very slowly. The models might need to be very, very wide to actually prevent forgetting completely. So maybe over-parameterization will not solve everything. I should say that their setup is somewhat restrictive. So this result doesn't mean that everything is solved. There's still a lot of work to do, even to move to more general feed-forward networks, and of course in convolutional networks and so on. And at future direction, we could mention finding stronger nonlinear models for studying over-parameterization, like feed-forward ones, but maybe with less assumptions or not the exact same setting as they use, the training setting. And we can ask other analytical or practical cases where forgetting really occurs in huge neural networks. And well, eventually, I don't know if it's possible. I have a feeling that it is, but hopefully we can get as a community scaling laws for forgetting. So we can eventually we will be able to say how much depth and how much width and how much samples and how much, a lot of questions we need to prevent forgetting. And this is would be a very, very strong result. We wanted to take a break, but I think time doesn't allow it. So we'll just continue. No, sorry, that's it. We are going to move to algorithmic methods to mitigate forgetting. You are probably aware of them. The first one is the regularization method, and then OGD, and then So I'll start with the regularization. Gene will continue with OGD and discuss some more gaps and summarize the entire tutorial. Starting with regularization, if you're not familiar with it, so let's do a really quick intro. Instead of just minimizing the first loss and then the second loss, we are going to add this regularization term that keeps us close in the parameter space, and hopefully staying in proximity to the previous parameters will help us prevent forgetting. Again, will help us prevent a significant functional change. And we hope that this is what will happen. By adding it, we will hopefully converge to the intersection between two tests, or more tests, of course. And 3 seminal papers in this field have been using diagonal regularization weighting. So if you notice, there are 2 important hyperparameters here. One of them is the regularization strength, and the other one is the weighting metrics for this L2 regularizer. And so 3 very important papers used a diagonal matrix for computational reasons, mostly computational reasons. And the first one was a paper by Kirkpatrick at 2017 that proposed using the Fisher information metrics of previous tests, but then they couldn't really do it numerically, so what they did is just use the diagonal of this metric. Another paper from Zenke et al., they decomposed the loss decrease while training the first task to contributions by different parameters, and they took each of these contributions as the importance of the parameter in the current task for the new task. And Aljundi et al. At ECCV 18 proposed another measure that used the gradient of the norm of the square norm of the output of the network. It's not really important right now, the specific okay. It doesn't really matter right now the exact formula, but they can try to assess this how much the current this specific parameter affect all the output of the entire network. And interestingly, in ASTAT 22, Benzing showed that you could link all these 3 schemes back to Fisher information. So not only the first one, but all of them are related to Fisher information of the syn tasks. And something that I find very interesting is that empirically, Lubana in CoLLAs 2 years ago and Smith in CVF 23 showed, and of course collaborator, found that empirically isotropic weighting is often competitive with these fancy methods from my lab. So even though a lot of the research effort has been put on these kind of heuristics, how to choose the weighting metrics, eventually, a few years later, people show that if you just take the identity metrics, it works quite as well on practical settings. So I think the only paper that really compared between isotropic ones and the proposed weighting metrics is the Kirkpatrick, but then the other one didn't, and also a lot of papers afterward didn't. And at least the message here should be that, well, you should compare to the isotropic weighting. Yeah. That wasn't the main message of their paper, so they didn't really discuss it. They just said, surprisingly, it happened. Mm-hmm. Yeah, that's an interesting point. I think they used actually big models, yeah, if I remember correctly. Yeah. Okay. Um, Analytically, we know that Fisher information-based weighting prevents forgetting in continual linear regression, but not in classification. We showed it in ICML 23. And Ivatani showed very recently that it does not, so Fisher-based weighting does not prevent forgetting when the Fisher matrix is approximated by its diagonal. So, analytically, there's justification to using maybe this entire matrix, but taking only the diagonal kind of loses some of its analytical benefit. Well, naturally, you use an approximation. Yeah. I think they just show an example. Uh, Makes sense. Um, Again, this wasn't the main part of the paper, just a section, but yeah, it's a good question. I should have consulted with you for the future direction. Ah, okay. Yeah, it's a good point. Maybe we can discuss it later. It's a good point. I think it's interesting, like from an optimization point of view, at least. Um, could you click on that? Okay. So the other important hyperparameter is the regularization strength. And well, naturally, it creates kind of a trade-off between stability and plasticity. And the reason is if you take lambda to be exactly zero, let's say, then you just minimize the current loss. You don't care about the previous task. And if you take lambda to infinity, then you just stay where you are. You don't care about the current task, and you just solve the new task. Okay. And some analytical finding that I want to mention is that people saw in two papers from CoLLAs, Les CoLLAs and ICML24 that carefully tuned strengths can sometimes, but not always, prevent catastrophic forgetting, and but specifically in noisy linear setting, linear regression setting, that are otherwise forgetful. And also, we found in a paper that scheduling the strength, so changing the strength, so it like dramatically increases or decreases, can actually harm the convergence guarantees that we got for in a very like for a fixed step size, not step size, sorry, regularization. Some future direction. So our work kind of focused on the weakly regularized case, so when lambda goes to zero. I'll soon say why we did it, but in very briefly because it's not analyzable otherwise. So we analyze this lambda goes to zero in linear classification and show that it's linked to again to projections like in the linear regression setting. And again, we ask whether we can extend these results to a nonlinear model. And again, back to the task recurrence part, if you prove that it's somehow connected to projections, then you would get some nice results from the projection onto convex sets literature, like convergence result for task recurrence. Um, the other thing that you might want to consider is to obtain better theoretical understanding of the weighting matrices and regularization strength. So for instance, why is the diagonal not a good approximation sometimes, and whether we can, even practically, how can we choose the weighting matrices better? And I think it's an important research question. Again, it's, you know, there are, I think, hundreds of papers on this kind of direction for like proposing different weight matrices. So I think it's important to understand even analytically. A side note before I pass the mic to Jean. Let's talk briefly on early stopping. We mentioned it earlier. So by now, I mentioned two settings where we had a closed form solution. One of them was when you start from the previous iterate, you minimize the current loss with SGD and you converge, which of course, like someone already commented, it's an unreasonable assumption. Like mathematically, you never converge, numerically, sorry, you never converge. You just can become very close to convergence, maybe to the zero loss. And the other part where we got a closed form solution was for the regularized setting. So if you have this L2 regularization, even though it might be weighted, you get a closed form solution. And of course, analytically, it's a very desired property. You know, if you have a closed form solution, you can analyze it. What people do practically is that you never converge for the unregularized case. You never converge, but instead you early stop. So you stop when the loss is smaller than some predefined epsilon, or when, for instance, after a fixed number of steps. And in stationary settings, there's a known connection that if you minimize, for instance, an exponential loss with gradient descent or SGD, and you use early stopping when epsilon goes to zero. So for a very small epsilon, then when in the limit that epsilon goes to zero, the direction converges to the direction of SVM. And then in a regularized model, so the same loss, but now we regularize towards the zero. And again, if you take lambda to zero, again, you converge in direction to SVM. Okay, so there's this connection. Interestingly, we found that in continual learning, it doesn't happen even in very simple linear models. So we haven't found yet a simple connection between those. We showed a negative result in ICML23, and Zhao et al. Showed in ICML24 some limited positive result that does connect regularization and early stopping, but it's still not solved. It's unclear what the real connection is yet. And now let's move to OGD.
All right, we will talk about the OGD briefly before lunch break. So I guess everyone here probably knows what is OGD, but to just give a brief recap, so it's to constrain the parameter updates to the subspace, which is orthogonal to the gradients of the previous task outputs. So imagine you again have a two-task space, two-task solution space, and you found the. Do we have a laser here? Oops, sorry. Okay. Actually here. So you found the solution from the first task space, and then now you want to go to the second task solution space. But then let's say you got this gradient here. But then once you take this gradient as it is, you're gonna escape from the first task solution. So what you do is you kind of make an orthogonal projection of from the previous gradient, and then you take only this direction component, and then you keep doing that. And the basic idea is that you can still retain the knowledge from the first task, but also be good at the task two. And this was proposed by Faraj Tabar in 2019. And then following that, Benani and and the colleagues showed that showed in analytical setting that this OGD in continual learning under NTK regime. Just a recap, in NTK regime, you have an infinite West neural network, and then you have a constant neural kernel, which can stay linear during the training. So in this NTK regime, you can show and prove that this OGD will gonna be robust to the forgetting, but with the infinite memory, which means that you can have as many memories from the previous gradients as you wanted, which is not feasible in real world setting. And this generalization is much tighter than simple stochastic gradient descent. And again, if you look at their bound in OGD, you can see that the terms are related with task similarities and the ordering, which again indicates that there is a room for the curriculum learning effect. But again, overparameterization assumption, especially not just overparameterization, but this infinite width assumption in NTK regime is critical in OGD robustness. But in large, this orthogonal gradient descent is one of the bigger family of the method, which employs the memory systems of the previous task knowledge. So before OGD, Lopez, Paz, and Raznato showed proposed the gradient episodic memory, and there is a difference between OGD and GEM. So in GEM, you take a gradient from the direct loss. On the other hand, in OGD, you take a gradient from the model logic output, and this and the efficacy of these two methods become more clear when you are at the convergence of the model, because as you are getting closer to the solution space, your loss becomes smaller, and then also the gradients then takes much smaller, and then it becomes less effective. And that was the motivation from the Faraj Tabar and the colleagues to propose this method as well. And long before, there is, again, this replay of the previous examples. So you basically show the previous examples from the previous tasks as a replay, has been proposed from the biological learning system of the hippocampal complementary learning systems long time ago. And these are the families of the method that people have used to mitigate the forgetting. Okay, so going back to this Lopez-Paz and Raznato's taking the gradient from the direct clause, Doan and colleagues showed the results from NTK regime, theoretical results from NTK regime, and compare the OGD and GEM. And if you look at the terms there, the only difference is that in GEM, you have the term from the residual. So residual means that the difference between the previous task and your current target task. And what this indicates is that when you're trying to make a projection of the gradient and use that to mitigate the forgetting, if you have the task which is well aligned versus current task, then this will going to affect less on what direction of the gradients that you're taking currently, which they remark as this can cause a unlearning of the specific task because that's less effective in your current gradient update than the other ones. So again, both of these studies are limited to NTK regime, and it is in general, I think, the limitation of the approach, and the field should find a way to deal with. And we will just talk about the thing that hasn't been really touched in theory, at least in our knowledge, is the replay. So although the replay or the interleaved training has been shown pretty effective in mitigating the forgetting, there is no theoretical work. But there is a hint from the Lee and the colleagues' work, which they show that the effect of EWC, the regularization method that we discussed, and the replay can be very different when you have a different task similarities. For example, when you have when you are in either very similar tasks, when you have very high task similarity or low task similarity, replay can be very effective. But when you go into this middle ground of task similarity, then replay becomes almost non-viable. And they again try to explain it between the balance between either reusing the node or activating the new node. And since this is since just giving an example from the previous task doesn't change their trade-off fundamentally, so replay cannot really help this training issue. So just as one word, there is no theoretical work in this word of replay. So I think that's like a big question for the theoreticians. And the other one is, again, going back to this large foundation models and the current way how we do the continual learning. So large foundation models are becoming increasingly common, and people, the common practice is to adapt those pre-trained models by fine-tuning. And there has been lots of new fine-tuning method proposed, for example, LoRa, where you don't take all the parameters to fine-tune, but you basically take the row rank decomposition and then try to effectively update only the relevant or the important parameters for that specific downstream task. And then if you try to link those fine-tuning and the lifelong learning or continual learning, then we don't, lifelong learning, there are already some of the evidences showing that this doing a continual learning on those pre-trained models are different because they have, for example, in terms of loss landscape, they have a shallower minima as the Meta and colleagues showed. But then the big question is how this different fine-tuning method can affect the continual learning. And in our knowledge, there is no theoretical understanding of how this different fine-tuning methods can affect different aspects of the continual learning, which remains as an important question. And finally, there is a new learning paradigm that people are very excited with. As you can see in all the posters here and also in the ICML before, there is this in-context learning happening. Which is another form of meta-learning. But again, I think there is a lots of theoretical work which should be done to understand in-context learning and how it is related to the continual learning. And there is an afternoon tutorial which we're going to deal with this, which I'm very excited with. All right. We're just going to make a quick summary. So we gave an overview of typical theoretical tools and approaches which can give you understanding of different aspects in continual learning. for example, projection method or using mean field approach, which can give you better understanding of the learning dynamics, not only after the training. And we discussed some of the phenomenology of catastrophic forgetting, and I think big overarching idea was that we cannot really think of one aspect and how it affects the catastrophic forgetting, but there is a complex interplay between different vectors. And finally, we presented few algorithmic methods for remedying the forgetting, mainly the regularization method, as Itay showed. And hopefully, I think you had the idea that there are lots of research should be done, also for the replay and the parameter isolation methods. So let us know if we miss anything important or any references. And those are our contacts. And thank you for being here.
Thank you very much. We do have some minutes if you have some questions. So we have a questions over there. Do you have a microphone, right? Yeah, great. Yeah, I will follow the order, the nearest neighbor first.
Nice tutorial. It seemed like one of your objectives is to bring more people into continual learning theory. Is that fair? Because you kept saying this. But I have friends who are theorists, and I don't think they're casting as wide a net as you in terms of what is theory. And I like yours better because you also seem to be including a lot of the empirical results, trying to analyze things and understand behaviors empirically or analytically versus only like my friend, I invited him to give a talk recently. He's like, theory is about two things, and he's like proven bounds, figuring out if we can fit our data, figuring out, generalization bounds. And he's like, that's what we do. There was nothing about empiricism. I don't think he's ever had coded anything for one of his papers besides to make plots. So can you say something about that? Like, what are your, because I think a lot of people, including myself, would be like, my lab's doesn't necessarily have the mathematical willingness to do a lot of theory work, I would say. It's a lot of work. But I can call myself a theorist if you're including that other stuff.
Okay. So first, to answer the question, I'm still doing my PhD, but I don't consider myself as a theoretician because I don't do that finding upper bound or lower bound and making a tightness more tighter or coming up with a proof. But I think, but my background is physics, and I think physics already gives you a very good historical example why those should come from the two directions, right? Because I think there are lots of interesting empirical phenomena that we discover from the practitioners. But then sometimes we get lost, right? There are lots of phenomena, but you poke here. I think there was like a really nice talk in ICML, which explained it in a very nice way. There's a huge elephant, and then a lot of us are poking in different parts of elephants and then say, oh, this is a column or this is a rope from the tail, but we don't have a very good understanding of what's going on. But from my side, I think what theory can offer is giving you just better direction where to go and try to encompass or try to explain all of this things that we see in a better way, and then trying to put in nicer way. I don't
know. We had some other questions from
if I may add one.
Oh, sorry. Go ahead.
Yeah. I do call myself a theoretician. Mainly because I'm from computer science and not physics, maybe. And not everyone in our group, but my research is mostly focused on bounds. And I think if you ask physicists, then this is not how you make great advances, like big advances. It's a different point of view on the world, I think. But I think many papers that I really love, like I mentioned one from Benzing at ASTAT 23, and even the the Mirzade's paper on overparameterization, there might be maybe observational in the sense that they take phenomenon, really try to understand them rigorously rather than proposing new algorithms. And some of them kind of like Mirzade explained, showed that the gradients become more orthogonal, and it's a really good explanation, I think, even though it's not considered analytical. But you could do really good progress in the phenomenology of everything and in the algorithms by not doing one line of math, one inequality, just really understanding model with some analytical inspired experiments, but experimentally even. Great. Theoretically inspired. Yeah. Okay, okay. Okay.
Hi, thanks for the tutorial. I have a question regarding this Goldfarb et al. 24 paper that you mentioned, where there is one case with highly over parameterized, and then there is like this non-monotonic curve, for getting peaks at intermediate task to similarity. And in the other case, when it is not over parameterized interpolation, it is near the interpolation threshold, then the forgetting is monotonic. So first of all, in the case of so you just show like high over parameterization, but I'm wondering in the case of, let's say, if you take the number of parameters and samples together to infinity, or just if you, in the limit of over parameterization, does the curve remain similar, or does the nature of the curve change? That is the first question.
Could you just repeat the last part? I'm not sure I understood what.
So
So you either take the number of parameters to infinity, or
if you keep over parameterizing more and more, does the nature of the curve change? Does it become just lower and lower in terms of the forgetting level? Or does the qualitative shape change as well?
I'm not sure. Sorry.
So you have this kind of a,
Yeah, we get this U-shaped behavior.
right?
And essentially, even if you take the number of parameters to infinity,
Mm-hmm.
if you compare it to the latent dimensionality,
Right.
then even then you get quite a considerable amount of forgetting when the tasks are intermediately similar.
Mhm.
So this is another case where forgetting does not diminish entirely when you are even infinitely over parameterized. But this kind of required us to use a similarity measure, a random similarity measure, and also in some sense the size of the latent space that we rotated was also infinite. Yeah. I can show you the technicalities later, but
I see. And the nature of these curves, like monotonic near interpolation threshold, do you have like, do you have a theoretical result that would predict this, or is it more empirical,
so
the nature of these results?
okay. This is entirely theoretical paper. I mean, the first few sections and the plots that I showed are analytical results. So we have an exact expression actually for the expectation. But we did see this also in some experiments in very shallow MLPs. But it's mostly an analytical result. And importantly, again, this happens only when the task similarity notion is random. So you kind of, in the expectation of all low dimensional permutation, then you get this result. Yeah.
I see. Thanks.
Other questions? Sure. Yeah, we still have time.
What do you think? So I understand why why we want to study things like deep linear models, but in terms of like catastrophic forgetting in linear classifiers. How much of that do you think we can actually generalize? Because I saw some of the papers being referenced. We're doing things like that. How much do you think we can actually generalize to deeper neural networks, where oftentimes a lot of the forgetting is in the hit latent layers and not in the output layer itself? So I don't know, of all the things that were presented, that's the one I'm like, I don't know if we're, because from a practical standpoint, so I would like to see the argument for what we might learn by doing that. Versus just saying, because if you're in just a linear setting, you can use alternatives that work maybe slightly worse, but don't catastrophic forget.
Thank you for the question. So we know from stationary settings, for instance, we have analytical results showing that deep models in whatever depth and with the homogeneous activation function, so for instance value, you do get this kind of projection property, but only in stationary settings. We don't have this result yet in nonlinear continual models. And I think, if you look back 10 years ago, first there was a result showing that linear models have this projection, this SVM convergence result. And then about even 10 or 15 years later, people were able to show that it happens also in nonlinear models. So we showed it in continual linear model. I hope, and I have a feeling that it does happen in continual nonlinear models. But I mean, I do agree that it will be more interesting in deep models. But like first you show it in linear models, then hopefully you could maybe show it in nonlinear models. But yeah, I mean, it's very hard. But I mean, no, it's also very challenging, and I think it's really rewarding. The paper that I mentioned in the stationary setting, like, was by very strong people, Wu et al., and I think a similar result in continual learning would really be revolutionary in the theoretical aspect.
Yeah, there's another question.
Hey, thanks. So to me, it always struck continual learning is somehow about constraints. Like, for example, you don't unstore all the data and retrain whenever a new task arrives on everything and so on and so on. So I'm a bit wondering, do you think there's value in maybe being more explicit about various costs, like storage costs, compute costs, or so? Or is there a trend of actually making that more explicit? Or do you think that's for these kinds of analysis not conductive to include that?
I hope I got the question right, because I don't know. The microphone is a bit low, but I think, okay, yeah.
Yeah, so what I mean is, I guess some of the continual learning problems, like forgetting, would completely vanish if you consider infinite storage and infinite compute.
Yeah, yeah.
Like whenever there's a new task, you retrain on everything from
Yeah.
scratch. And so there are always constraints that we are kind of considering, but often not on a scalar level, like Pareto funds of how much compute you spend on something and so on. Do you think there's value in looking at that more closely?
Yeah, at the constraints. Yeah.
The constraints, instead of just, oh, we have a storage constraint, but it's a bit like binary, basically, instead of considering it on a soft scale.
So it's a good question. Most of the algorithms that we mentioned were like plain SGD. So no extra memory, no other resources. In optimization, for instance, once you just allow an order of the extra memory, then one thing you could do, instead of using the last iterate, so just the result from the last task, using the average iterate, you already get much better convergence guaranteed. But if you look to the future for nonlinear models, then maybe this extra memory can be very expensive. And one other thing is that for instance, in replay method that Jean mentioned, then I think it's a good starting point for theoretical research on these constraints. So in replay method, you add a buffer memory, And now a very basic question, I think, theoretically, and also you could check this empirically and see what happened, is how large should the memory buffer be? Like, and how large should it be depending on the test similarities, depending on the pre-training method, depending on a lot of stuff. So I do think there's a lot of place for such research.
I think so. There are two literatures that I included for the OGD part, Benani and Duan, and I only included the very basic. I mean, not basic, very amazing proof, but like just show that it is provable that OGD will gonna convergence. No forgetting when you don't have this memory like storage issue. But if I'm correct, in Duan's paper they have this factoring issue when you have a limited memory buffer. So just to answer your question, I think people in the theory side are aware of some of the realistic settings constraints and so on. But I think, again, as we introduced in the very beginning, you start with the simplest model, and then from there, you were going to add those constraints. But I think it's important thing that we need to consider for sure when you develop a theory.
I had one question as well. Sorry, building on the question that York did, but I don't think anyway. So like in RL, there's this growing community in like the theory of continual reinforcement learning, of like thinking about capacity as the reason why you need continual learning. So you have this capacity bound agents, and then because you can't store everything that they see, then you have to do continual learning. And I kind of disagree with that. I don't think that you see continual learning because of capacity. I think it'll happen whether you have capacity or not. But I wanted to know sort of what your take is. Is it sort of capacity in the architecture to store information? Is that the bottleneck, or are there other things that actually leads to continual learning problems?
I would really appreciate if you could be my reviewer in all future papers, because our paper that I mentioned kind of assume that there exists a perfect offline model. So if you see everything in an offline setting, you can perfectly solve it. And if you think about some tasks contradicting each other, or even a capacity bound like a restriction, like you mentioned, then yeah, so a lot of the theoretical papers do not apply anymore, and you should make other assumptions and other type of analysis. But I'm sure everyone, like, there are a lot of practitioners here which might are better familiar with it than I am. But I don't think the limitation currently is the capacity. Like if you train in, let's say, in a multitask training method, then usually you could solve it. Like the networks are very big currently, and we kind of as a community allow very large foundation models even. So if you train everything at once, you usually succeed in a multitask with a multitask algorithm. So I don't think capacity is the correct way to look at it. But of course, you could always handily design specific settings where it is the capacity, the problem.
Okay, let's thank the speakers again.